So we're going to take a look at a few different situations that happen with triangles where we draw perpendicular bisectors of the sides, and then we're also going to look at if we draw the bisectors of each angle in the triangle, and some geometrically interesting things that happen when we do that. So we're going to kick it off by looking at the perpendicular bisectors of a triangle. So if you look at this picture here, you're going to notice that there's a lot going on, right? This picture is kind of complicated. There's marks everywhere. But what's happening is, if you look at each side, let's look at segment AB, for instance. Segment AB has this segment, this red dotted line segment here. Let me trace over that maybe in a color that's going to be a little bit easier for us to see. All right, so now we got this purple segment that's coming over here and intersecting segment AB at point J. That segment is segment AB's perpendicular bisector. It is perpendicular to it, and you can see here J is the midpoint because from J to B is congruent to from J to A, segment JA. So this is the perpendicular bisector of segment AB. That would be, I guess we could say that that is segment PJ, right? Segment PJ is the perpendicular bisector of segment AB, and then segment PK right here is doing the same thing to segment CB. So segment PK is the perpendicular bisector of segment CB. It's perpendicular to it, it's bisecting it. And then we can look at segment PL right here. It is the perpendicular bisector of segment AC. It's perpendicular to segment AC and it's bisecting segment AC. So those are our three perpendicular bisectors. And this theorem says that they are concurrent. And what that means is that they all intersect at one point, which is unique because I have three different segments. If I'm looking at two segments that intersect, of course they're going to intersect at one point. But if we start looking at more than two segments and where they might intersect with each other, it's not going to be guaranteed that three segments will always intersect at a single point, right? If I just sketch out three segments up here, I could sketch out a segment like this, I could sketch a segment like this, and then when I add a third segment into my sketch here, it's not guaranteed to go through that same point, right? It could look like this. So the fact that these three perpendicular bisectors all intersect at one point, that is, I would say, geometrically interesting. And that point, what's even more interesting is that point there is equidistant. It is equidistant from all three vertices of the triangle. So what does that mean in our picture, right? If we have this picture here, what can we conclude when we have these three perpendicular bisectors all intersecting at point P? Well, it means that point P, the distance from there to A, and there to B, and point P to C, they're all the same distance. That's equidistant from all three vertices. So we would be able to say that distance from P to A is equal to the distance from P to B is equal to the distance from P to C. So that is this theorem 5-5, the concurrency of perpendicular bisectors of a triangle. That point P would be same distance away from all three corners. It's the place where the three perpendicular bisectors meet. That point has a special name. It is called the circumcenter of the triangle. The circumcenter of the triangle. So every triangle has this special point, sometimes inside it, sometimes outside it. We're going to look at when they might happen, one way or the other. But every triangle has this special point called the circumcenter, and it's the place where the three perpendicular bisectors of it meet. Now, I got a question here that says, how can we prove that this must be true? How can we prove that point P is same distance away from all three corners? Well, it goes back to something we learned about in the previous section, that any point on the perpendicular bisector of a segment will be equidistant from the endpoints of that segment. So since point P is on the perpendicular bisector of segment AB, right? P is on the perpendicular bisector of segment AB, which tells us that from P to A has to be equal to from P to B. The theorem we learned in the previous section says that that point that's on that perpendicular bisector, it will be equidistant from the end points of that segment. But P is also on the perpendicular bisector of, let's say, segment BC, right? It's on segment PK, which is the perpendicular bisector of segment BC, which would tell us that from P to B is equal to from P to C. Now, if you look at these two statements, PE equals PB, but PB equals PC, that means that the distance from P to A, which is equal to the distance from P to B, but the distance from P to B is equal to the distance from P to C, that's that statement that we just wrote up here. That's kind of how we know that this idea has to be true. It all goes back to that theorem about the points on the perpendicular bisectors of segments being equidistant from the endpoints of the segments. Now, there is one more kind of interesting fun fact about this idea of the circumcenter, that for any triangle, there will be one circle that you could draw that would go through or contain all three vertices of the triangle. There would be only one triangle that could do that. And the triangle that would do that is called the circumscribed circle of the triangle. So in other words, what we're saying here is if I drew some random triangle, right? Let's just use this little spot here. And I just sketched out some triangle like that. There's only one triangle one circle that I could draw that would contain that would go through all three corners. And if I was trying to eyeball it, maybe it would look something like, this is kind of tricky here. It would maybe look something like, maybe about like that. I think that looks pretty close, right? It contains all three corners of the triangle. That circle is called the circumscribed circle of the triangle. It's unique to that triangle. There's only one that would do that. The circumcenter of your triangle, the circumcenter, is the center of that circle. So if we were to scroll up here real quick and look at this triangle, if I were to take a compass and center my compass on point P, and then extend it out so that the compass width was like from P to B, or P to A, or P to C, because those should all be the same, right? Put the pointy part of my compass here, center my compass out here. There would be a circle that I could draw. The circle that I would draw with that compass setting should go through all three corners of that triangle. That would be called the circumscribed circle for the triangle. Now, I mentioned just a few minutes ago, I briefly mentioned the idea that every triangle has a circumcenter. Sometimes it's inside the triangle, sometimes it's not. Well, let's look at the three possibilities for where that circumcenter could be located. If I am looking at an acute triangle, and I just try and sketch out these perpendicular bisectors. So I'm going to sketch out the perpendicular bisectors of this acute triangle. The first thing I'm going to do is I'm going to get an eyeball, an idea where the midpoint of each side is, because I know that the perpendicular bisectors is going to go through the midpoint. So let's say that's a midpoint. Looks like maybe that's a midpoint, and about here is the midpoint. And then if I draw a segment or a line perpendicular to each side at that midpoint, so let me just mark that I'm indicating that those points are the midpoints. Now if I sketch out, let's see, about like that, and then so that's a 90-degree angle, and then maybe about like that, so that's a 90-degree angle, and then maybe about like that, so that's a 90-degree angle. You can see that circumcenter, that point where those three are intersecting, is inside the triangle. And that's going to happen for every acute triangle. Our circumcenter will be inside the triangle. Now, I maybe have a right triangle where one of my angles is 90 degrees. Well, let's look at the three perpendicular bisectors here. So first I'm going to kind of eyeball where I think the midpoints would be, maybe about here. And then for the hypotenuse, maybe about right here. And then if I start sketching out what looks to me like the perpendicular bisector, so I come through here, maybe make a 90-degree angle like that, make a 90-degree angle like that, and then I make a 90-degree angle like that, you can see that that circumcenter is actually at the midpoint of the hypotenuse. So it is on the triangle. Specifically, it is the midpoint of the hypotenuse. So in a right triangle, your circumcenter is the midpoint of the hypotenuse. Now in an obtuse triangle, let's look at where our circumcenter might end up. So again, I'm going to kind of eyeball the midpoints of the sides. Looks to me like about there. And then this one looks to me like about right there. And then maybe about right, let's see, probably about right there. Okay, so now if I start drawing these perpendicular bisectors, like that, maybe like that, and then like that, you can see that the place where they intersect is actually outside the triangle. So in an obtuse triangle, our circumcenter will be outside the triangle. Just an interesting little, I guess, characteristic of the location of the circumcenter. Acute triangles always have the circumcenter in the triangle. Right triangles always have it at the midpoint of the hypotenuse. Obtuse triangles always have the circumcenter someplace outside the triangle. So that is the concurrency of the perpendicular bisectors. Now we're going to take a quick look at the concurrency of the angle bisectors of a triangle. So if we look at this picture and just kind of digest for a second what's going on, we see we have triangle XYZ. And then I want you to take a look at this segment right here, going from X to this place right here, which would be Q. It's hard to tell the way this drawing is made, but that segment is bisecting angle YXZ. It's cutting it into two equal parts. So segment QX is the angle bisector for angle YXZ. And then segment QY is the angle bisector for angle XYZ. You can see this part is marked congruent to this part. And then segment QZ right here is the angle bisector for angle YZX. It's divided angle YZX into these two congruent parts. Now you'll notice, of course, now that you know what concurrency means, that those three angle bisectors are all meeting at Q. So the angle bisectors of a triangle are concurrent at a single point. And that point is equidistant, not from the corners of the triangle like the perpendicular bisector's point of concurrency was. We can actually look at that, right? It's clearly, if you look at where Q is in relation to the corners, it's clearly closer to, like, let's say Y than it is X. So it's not equidistant from the corners or the vertices. What it is equidistant from, it is equidistant to the sides of the triangle. It is equidistant to the sides of the triangle. So we look at this picture here, and we can see that from Q to N is a segment that is perpendicular to the side YZ. So we always measure, we talked about this in a previous video, that if we wanted to measure the distance that Q is from this segment, YZ, we're going to measure along a path that is perpendicular to the segment, right? We're going to go straight over to the segment, not measure at some kind of path that kind of hits that segment at a non-right angle. So segment QN represents, the length of that segment represents the distance that Q is from this side, YZ. That length, QN, would be equal to QO, because QO is the distance from Q to this side of the triangle, because segment QO is perpendicular to segment YZ. So QN is equal to QO. It's also equal to QM, because segment QM, you can see that it's perpendicular to segment XY. So the length of that segment would represent how far away Q is from segment XY. So according to this theorem, point Q, which is the point of concurrency for the angle bisectors, would be the same distance away from all three sides. So in our picture here, QN would be equal to QO, would be equal to QM. That point is also has a name, just like the circumcenter was the name for the concurrency point for the perpendicular bisectors. The concurrency point for the angle bisectors is called the incenter of the triangle. It's called the incenter. And just like the circumcenter was the center of a special circle for this triangle, there is a special circle for this triangle that the incenter would be the center of. And that's the circle that intersects each side of the triangle exactly once. So if you were looking at a triangle, or if you were looking at this triangle, I could draw lots of circles that would intersect the sides multiple times. Right? Sketch out a circle that would look maybe like that, right? Let's try to do that a little bit better. Not very circular, but you get the idea. So that circle there you can see is intersecting each side of the triangle two places. Here and here, here and here, here and here. So it's intersecting each side of the triangle in two places. There is one circle that I could draw that would intersect each side of the triangle in exactly one place. And it's called the inscribed circle of the triangle, right? And the incenter is the center of that special circle. So it would look like, if I was going to try and sketch that out, let's try and sketch that out. That triangle, that circle would look more, to kind of explain it the way I explained the circumscribed circle, I can imagine taking my compass and putting the pointy part at Q, and then stretching it out so that the pencil part of my compass was either at N or M or O. Should work either place because those 3 points should all be the same distance away from Q. So I'd stretch that compass out so that it was from Q to O or from Q to N or from Q to M. And then if I drew that circle, it would maybe look something like this. If I can sketch that out fairly accurately, it would maybe look something like that. And you can see that that's just intersecting each side of the triangle in one place. It's just hitting the side as it comes by on all three sides. And that would be called the inscribed circle for that triangle. So circumscribed circle hits the corners each hits each corner once. The inscribed circle hits each side once. And that happens, that circle has its center at the incenter.